Okay, today in this talk, I'm going to explain hub and spokes model for governmental data, for data linkage and data security. This is Statistics Korea's hub and spokes model for safely linking and using governmental data. Here, statistical registers play the role of hub, while diverse, scattered data are linked to the hub through spokes. To guarantee security of the linked data, Statistics Korea plans to leverage modern privacy-preserving tools such as homomorphic encryption, differential privacy, and synthetic data. A pilot project has been implemented to link scattered data on small businesses in their encrypted state between our Statistics Korea and separate Gyeonggi province. The pilot project demonstrates that homomorphic encryption and key sharing scheme has potential to facilitate data cooperation between governmental agencies who do not necessarily trust each other. So the contents are, first I'll briefly explain the background, and then I'll introduce K-statistics system as a hub and spokes model, and then I'll introduce some applications. Background first. Nowadays, we face diverse data. For example, in our Statistics Korea, we have traditional survey and census data, but at the same time, we are faced with increasing amount of administrative data coming from other agencies. And on top of that, we also face digital big data. Institutionally, Korea has passed 3 Data Acts in December year 2019. So hereafter, we are expecting large amounts of data are expected to be linked and utilized. Thus, we can enjoy so-called economy of scale and economy of scope in using data. Nowadays, big data combined with big models. So obviously there is complementarity between the size of data and the size of a model. As data size is increasing, the model size is increasing as well. And big computing is supporting the marriage of big data and big model. So these 3 bigs are generating something big in real life. That's the world we are living in. Naturally, privacy protection issues arise. Regarding these issues, neither anonymization nor pseudonymization is sufficient for preventing re-identification. The risk of re-identification increases as more pieces of information are linked. So on one hand, we are in huge demand for linking different data to enjoy so-called scope or economy of scope. But at the same time, on the other hand, the risk increases. So this is related with the familiar 20 questions problem. Also, the cause of dimensionality problems in non-parametrics in statistics. So let me take an example. So in the population, we have A people, number 1 through number A. Number 1 his name is John. So in the first, as a first feature, we are using gender, so male, female, and then all the other numbers are males and even numbers females. So John is on the left-hand side. And then by using age, we are classifying whether young or old. John is young, so still John's identity is protected because the set size is 135. So it satisfies K anonymity, so-called, with the value of K being equal to 3. But by adding the height dimension, John is short. Therefore, John is singled out. So by using just the 3 pieces of information, the identity of John is broken. So these a series of three questions identify John. So in this example, as information on gender, age, and height is sequentially combined, the number of persons in each cell rapidly decreases. So John is identified after the third question. If you recall the previous example, here we are using minimum bits of information, left or right. That's like a single bit, 0, 1 bit. So that's the minimum piece of information. By using 3 pieces of minimum possible information, we re-identified John. I'll explain the same problem using the graphs. So if you just look at gender axis, John's identity is not revealed. If we add another dimension of age, still John's privacy is protected. But by adding the third dimension of height, John is singled out. So John's identity is not preserved, is not protected. This is exactly the same kind of problem, so-called cost of dimensionality in non-parametric statistics. As the future space is getting higher and higher, the number of observations falling in particular cell shrinks very rapidly. In the end, you cannot reliably estimate any function based on that few observations. In this example, that's exactly creating cost of dimensionality in privacy protection. As you see, as the dimension is getting higher and higher, the number of observations satisfying joint conditions is shrinking. In the limit, each cell is either empty or just contain one person. Therefore, single person's identity is revealed, as in this example. So as you see, traditionally, we are facing trade-off between bigger linkage and higher protection. So you have only one of two choices. One is if you go for stronger linkage, the protection is becoming weaker. The other option is you don't go for strong linkage. In that case, you enjoy strong protection, but the data value is not high enough. In this trade-off, pseudonymization and anonymization is not the best alternative, as you can easily see. So K-statistics system is a hub and spoke model for governmental data. So the current status is data are scattered across diverse public and private institutions, and we lack cooperation and trust among data owners, and we lack standardization in data format, and we face differences in data storage. So in the future, we are going to tackle all these problems, and at the same time, we will increase the linkage and will at the same time increase data protection. So we have two versions of K-statistics. In the first version, we link different data using Statistics Korea's statistical registers, so-called. And then the data protection is guaranteed through hardware protection. So by linking and analyzing data only in hardware protected data room, we can protect the data security. But in the future, in K-statistics version 2, we will go beyond the hardware protection by using software protection, including homomorphic encryption, differential privacy, and synthetic data. So here comes K-statistics. Nowadays, many people, including media, are using the term water dam. So the left-hand figure demonstrates the structure of water dam. So in this world of them, the data are coming from nowhere and everywhere, and then they are mixed together, and we don't know who are using this data. So we lose control of data ownership, and at the same time, we lose control of data privacy. According to K-statistics system depicted on the right-hand side, we safely protect each data holder's data, and then we safely link those data. So if you compare these two diagrams, then on the left-hand diagram, there is no order, but on the right-hand diagram, the data are protected and linked in an orderly and safe manner. I can explain the same concept using a spreadsheet. So imagine a huge spreadsheet. So each row corresponds to different observation unit, and each column corresponds to different features, different characteristics, different variables. So as of now, different informations are owned by different governmental agencies. For example, income data are owned by the Korean version of Internal Revenue Service, IRS, and education data are owned by Education Ministry, employment by Labor Department. So as you see here, blocked by dark vertical bars, they are blocked, and it's not easy to link the blocked pieces of data. If you look at the bottom spreadsheet, different organizations don't have to trust each other. They better trust modern privacy preserving technologies like homomorphic encryption, so they can link and join their data in encrypted state. So thereby, without revealing their own information, they can cooperate. That's the scheme we have in mind. This is another way of explaining hub and spokes model. So in the center, there are statistical registers. So whether it's individual or household statistical registers, or child household registers, or business registers, those registers are located in the center as a hub. And then different pieces of information owned by diverse governmental agencies or public institutions or even private institutions are linked to the hub through spokes. And by using data in this manner, we can analyze reality from a comprehensive angle rather than separate angles. I will explain K-statistics version 2. So version 2 means protecting data privacy using modern privacy preserving tools, thereby allowing data analysis becoming possible outside of secured data rooms. So for privacy protection, we are going to use homomorphic encryption, differential privacy, and synthetic data. You are all familiar with the homomorphic encryption, so I don't have to spend too much time explaining this concept. So on the homomorphic encryption and computation are commutative. Therefore, you don't have to decode the data for computation. You can only decrypt the data after computation. So this advantage of homomorphic encryption. And obviously, you need to set up key management scheme for encryption and decryption of data. So here is one scheme for encryption and decryption. So imagine that there are two agencies like Statistics Korea and Gyeonggi Province. So they are two separate governmental agencies and they don't necessarily trust each other. So here we denote them as A and B. So A and B generates his or her secret key, so-called sk.a and sk.b. And then there is a trusted third party. The third party receives these secret keys and generates a public key corresponding to these two secret keys and only shares the public key with A and B. Then each data owner A and B encrypts his or her data using the common public key, PK, and shares the encrypted data and analyzes the shared encrypted data. Each agency A and B partially decrypts the results using her portion of secret key, SKA or SKB, and exchanges the decrypted share with the other party. And then each agency gets the finally decrypted results by combining his own partially decrypted share with the other's partially decrypted share. This is the scheme. Okay, let me explain this scheme graphically. So there are two individuals, agency A and agency B. Each agency generates secret keys, SKA and SKB. And then trusted third party, after receiving these two secret keys, combine the secret key and then public key corresponding to the combined secret key. And then after receiving the public key, each agency homomorphically encrypts their data, DBA and DBB, and then shares the encrypted version of data. So we have common encrypted data, which I denote h.encpk parenthesis db. And then each agency analyzed shared encrypted data and then got encrypted results. These results are encrypted, so privacy protected. And then each agency, by using his or her own secret key, each agency partially decrypts the results and then exchange the partially decrypted results. And then by combining own partially decrypted results together with the partially decrypted results received from the other party, they can finally obtain the final decrypted results. So this is one scheme. Let me explain differential privacy. The basic concept is recording the signal contaminated by some amount of noise. So let me explain global differential privacy first. So in this example, we have macro information, so-called overall mean. But in one case, the overall mean is obtained from 100 individuals. In the other case, the overall mean is obtained from one person less. You believe that the overall mean is privacy protected, but as you see in this example, by comparing two global means, you can identify the missing individual's individual income. So to protect this kind of information leakage from happening, you can add small amount of noise to the final aggregate average value. Then by controlling the size of final outcome, you can not terribly contaminate the final outcome, but you can protect the individual value because the individual value, the error size increases by 100 times. Let me explain the differential privacy using one example. So if you ask a question, have you ever used illegal drug last year? Responses will be hesitant. So to get the truth from the respondents, you can design a randomization scheme. So let them toss a coin. If it ends up tail, then they will say yes. If it ends up head, then they will tell the truth. In this case, you can protect the individual response, but still you can identify the overall proportion of illegal drug user last year. I'll skip the computation. And the second illustration is taken from Raghunathan's presentation, which is available on YouTube. So if we compare the original pixel image and the contaminated pixel image, the pixel images are contaminated by flipping each pixel with 25% chance. But still, overall, you can identify that the person depicted is obviously Mona Lisa. Local DP is used by Google, and global DP is used by US Census in year 2020. Synthetic data, that's the third piece of case statistics version 2. This is artificial data. That's not, which is not the original data, but has characteristics similar to the original data. Encrypted data are obviously heavy and inconvenient for analysis. So we provide synthetic data for practice opportunities. And then after enough practices, people can estimate the final model using the original encrypted data. So that's the scheme we have in mind. So let me go over applications. So by using statistical registers, you can do many things. So I'll skip this part. Currently in Korea, we are in the process of compiling comprehensive pension statistics. Korea is ranked #1 in terms of aging speed and old age poverty, but still we were not successful in compiling comprehensive pension statistics because different pieces of public and private pension information is held by different governmental and private institutions. We are currently compiling and combining all the private and public pension information using Statistics Korea's statistical registers. This is a spreadsheet version of what we are doing. This is a homomorphic encryption application. So we are going to conduct survival analysis of small businesses. And this is a joint project with the local government, so-called Gyeonggi province in Korea. So we compare encrypted results with plain text results using for some descriptive statistics on small businesses and logistic regression results as well. The sample size is 8,576 franchises serving Korean foods in Gyeonggi province. An establishment survival or death is recorded as a 0 or 1 every month during existence. So which results in a sequence of binary data which is suitable for logistic regression analysis. So this is how we change survival record as a sequence of survival indicators. We combine data scattered across two different governmental agencies. One is our Statistics Korea, the other one is Gyeonggi province, a local government. These are basic statistics, yearly births and deaths of shops over year 2015 to 2020, and yearly births of one-person shops. I will skip this information. And then we computed yearly turnover and yearly shop space using plain text as well as in homomorphic encryption state. And I also indicate the time taken. So basically, there was no difference between plain text computation and computation on the encrypted state. Also, let me mention that for these computations, we use Heian encryption scheme. And in that process, we got a lot of help from Professor Jung-hee Chun and his team. I appreciate their help. Logistic regression. The optimization process is basically iterative process. So from initial estimates through updating scheme, we get new estimated, and we repeat this process until convergence. So dependent variable here, YIT, is the survival indicator for firm I in year T. So survival is recorded as 0, and this is recorded as 1. And covariates include type of business district, sales in previous year, and the dummy variable indicating whether it's a one-person shop or not, also shop space, and dummy for COVID-19 period, which correspond to March 2020 and thereafter. For logistic regression, obviously this is a nonlinear function. So to handle nonlinear function using polynomials, we approximated using Chebyshev's n-degree polynomials from up to 63 degrees. And as you see in this graph, the original logistic function and its approximation look pretty similar according to our naked eyes. And these are the results. For many establishments, shop space and turnovers have missing values. So as a statistical technique to handle missing variables, we define dummy variables indicating whether the information is available or missing. And then whenever it's available, we interact that dummy variable with the variable of interest. So as you see, we have results reported in 3 columns. The first column is plain text results using the original logistic functional form. The second column is the plain text results obtained after approximating the logistic function using the Chebyshev polynomial function. And then third column is homomorphic encryption version based on Chebyshev approximation. As you see, the difference between first column and second column is arising from the functional form approximation. And the difference between second column and third column arises from whether you use plain text or homomorphic encryption. If I focus on the difference between second column and third column, as you see, there is no difference, which means that whether you compute in plain text format or on the homomorphic encryption, there is no difference. So let me explain these results if you are interested in. Establishments with any missing data face a higher death rate. Establishments with either a bigger sales amount or a bigger shop space face a lower death rate. Shutdown rate is high in developed business districts. Developed business districts are popular city centers. So in that case, turnover rates are pretty high. And rather surprisingly, shutdown rate is lower during the COVID-19 period, which is a little bit counterintuitive. But if you listen to shop owners crying that there is no alternative during this tough period, they cannot shut down their own shops. So the results are comparable with their cries. And these are the results reporting the life stage effect. So we define several dummy variables indicating life stage, grouped by 3 months. So first 3 months, next 3 months, and so on. And as you see, the death rates are lower during 9 months after birth, after establishment of new firms. And then they face higher death rate from year 1 to year 3 before finally stabilizing after 3 years. So this kind of life cycle pattern of small businesses doing business in Gyeonggi province in Korea. Now let me highlight a few more applications. Healthcare information. We are currently reviewing this application. In Korea, the medical data is, I think, quite high in terms of quantity and quality. But still, we face difficulty in sharing individual patient data due to privacy issues. So if individual medical data are further linked to family lineage, I think the Korean data would be ideal for at least research on genetic disease. And once we complete K-statistics version 2, I think we can achieve this goal. So let me summarize. Korea has high quality public data, and legal and institutional infrastructures are pretty good. As I said, we have already passed 3 data acts, and we have introduced regulatory sandbox to promote the usage of data, And in Korea, the technology infrastructure is pretty good. We are strong in ICBM, IoT, cloud, big data, and mobile in all 4 areas. And I strongly believe that there is a strong complementarity between data usage and data security. So by increasing the data security through the use of homomorphic encryption and other privacy preserving tools, we can speed up the data accumulation and data usage. Thank you very much.